In this video, we're going to look at solving equations that involve exponential and logarithmic expressions. I'm going to give you two methods for solving an exponential and two methods for solving a log equation. You can use either. I will never ask you to do one specific way or the other. The first way is that we're going to convert from exponential notation to log notation in order to isolate the variables. So this one we're starting with 4 to the x equals 64. So I'm going to convert my notation. If you need to use the spiral to do that, you can do so. So this becomes log base 4 of 64 equals x, and now my variable is isolated, and then I can do log base 4 of 64 on my calculator, or if you can do that in your head. So we'll get x equals 3. The other way to look at solving this equation is to start with the same equation, 4 to the x equals 64, and we're going to take the log of both sides. We can take the common log, the natural log, or log of any base. We typically use common log or natural log because that's what we can do on our calculator. So here I'm just going to use common log, so I'm going to do log of 4 to the x equals log of 64. Then we're going to use our properties of logs right here with our exponent and move this to the front. So this is x log of 4 equals log of 64. And then I can just isolate my variable by dividing both sides by the log of 4. So then I end up with x equals the log of 64 over the log of 4. Using the change of base theorem, that's just log base 4 of 64. So you could put it in your calculator either way, and again, you're going to get x equals 3. On the calculator, we can just graph 4 to the x minus 64. I'm just moved everything to one side to set that equal to 0. Then I can take a look at that graph there, and then I could find that 0, or if you prefer, you can put the 0 into your y2, and then just find that intersection. So second trace intersection, and you get the x equals 3 again. So several different methods there. So looking at a second example, both ways again. Remember, you just really need to know one way as long as you can solve a log equation. That's all I'm concerned about. So here we're going to start with 1.5 to the x minus 2 equals 100. We're going to do the converting method here. So this would be log base 1.5 of 100 equals x minus 2. And then we have to get the x by itself, so then we're going to add 2 to both sides. So this is going to be 2 plus log base 1.5 of 100 equals x. We get about x equals 13.36 here. Using our second method, we've got 1.5 to the x minus 2 equals 100 again. We can take the log of both sides. Here I'm going to use natural log just to show you that either one is possible. So we're going to do natural log 1.5 to the x minus 2 equals natural log of 100. Using my power rule, I'm going to move the x minus 2 to the front. I'm going to put it in parentheses just so we remember that that is an expression that needs to be kept together. And then we have natural log 1.5 equals natural log 100. So I want to divide both sides by the natural log 1.5 before I deal with that x minus 2. So this cancels out. Then I have x minus 2 equals the natural log 100 over natural log 1.5. Then we can do add 2 to both sides. So we end up with x equals natural log 100 over natural log 1.5 plus 2, which will again give us 13.36. So we can take a look at that graph. In my window here, I'm not seeing anything, so I'm just going to do a zoom out to see if that helps. Then I can see my exponential function, and again, then I can go find that intersection. So second trace intersection, and we got the 13.36 again. So now working with a log equation, we're going to again give you the two different methods. So we're going to start with, here we have log, remember this is base 10 because that's a common log, so I'm going to write that in there. So log base 10 of x equals 3. Here we're going to do our converting notation. So again, this is 10 to the third equals x, so 1000 equals x. Over on the other side, we're going to start again with log base 10 of x equals 3. Here we have to do the same thing to both sides of the equation. In this case, that thing that we have to do to both sides of the equation, the operation that we're going to do, is to create an exponential on both sides with the same base as the log. So our log has a base 10, so we're going to write both of these as an exponential, 10 log base 10 of x. And then on the other side, we're going to go 10 to the third. Here, the 10 to the log base 10 power are inverse operations, so they cancel each other out. So then we end up with x equals 10 to the third, which we know is 1,000. It's important to remember when solving log equations that you can have extraneous solutions. Remember that your argument on a log equation has to be a positive value. So if the value that you come up with solving algebraically is going to make your argument negative or 0, then it's going to be an extraneous solution. So always check your answers. We can also solve this by graphing. So again, I moved everything to one side of the equation, log x minus 3, and then I set that equal to 0. Taking a look at the graph, it appears that there's an intersection way out to the right here, so I'm going to change my window setting. We know what it is, so kind of helps us out here, and we can make this 5,000. Then you can see your intersections, so we could do second trace intersection, and I get my answer of 1,000 again. Here's an additional example here. So we're going to go log base 7 of x equals 2, converting notation, 7 squared equals x, so x equals 49. When I plug 49 in for x, my argument's going to be positive, so I feel like that's a viable solution. So over here again, we're going to do log base 7 of x equals 2. Remember here we're going to create an exponential on both sides, so 7 to the log base 7 of x equals 7 to the second power. So here these are the inverse operations that will cancel each other out. X equals 7 squared, which is 49. Again, 49 is going to keep my argument positive, so I feel comfortable with that answer. You could also solve by graphing any of these, so you always have that option. A lot of times you're going to have to adjust your window settings though. So looking at a few more examples here. Our previous examples were very basic functions. So here, remember, we've got the 20. So before we even use any of the procedures that we just talked about, we want to isolate the log or the exponential. So the first thing I'm going to do here is divide both sides by 20, and that's going to give me 1/2 to the x over 3 power equals 5 over 20, or 1/4. And then you can use either method that you want, so we can convert notation and make this the log of base 1/2 of 1/4 equals x over 3. Multiplying both sides by 3, we're going to get x equals 3 log base 1/2 of 1/4. If on the other hand we take the log of both sides, we can say this is log of 1/2 to the x over 3 power equals the log of 1/4, and then we'll get x over 3 log 1/2 equals log 1/4. Then we just have to do the rest of the algebra. So divide both sides by log of 1/2, and then we're going to have to multiply both sides by 3. So we end up with x equals 3 times the log of 1/4 over the log of 1/2. Using the calculator to solve either of those, we can see that x equals 6. Here we have another example. This one's a little more complicated. So the first thing I'm going to do is multiply both sides by 2 here. So we get e to the x minus e to the negative x equals 10. Remembering what negative exponents mean, we can write this e to the x minus 1 over e to the x equals 10. And then we don't want to deal with that variable in the denominator, so we're going to multiply through by the denominator of e to the x. So we're going to multiply every term by e to the x. So we'll end up with e to the x squared minus 1, because these will cancel out, equals 10 e to the x. Now I have a quadratic, so I'm going to move everything to one side of that quadratic, or one side of that equal sign, so it's equal to 0. So we have e to the x squared minus 10 times e to the x minus 1 equals 0. So remember, once I have a quadratic, I have multiple ways to solve that quadratic. So we can factor, we can complete the square, we can use the quadratic formula. So here we're going to say e to the x, I'm going to use the quadratic formula, is negative b, so 10 plus or minus b squared, so that's going to be 100 minus 4 times a, so that's just 1 here, times c, which is negative 1, over 2 times a, which is 1. So this gives me 10.1 or negative 0.1. Now remember, that's still e to the x equals these, so e to the x equals 10.1 or e to the x equals negative 0.1. And then we can solve those using our logarithm procedures. So if we do the convert notation here, we get log base e of 10.1 equals x, or over here we're going to get log base e of negative 0.1 equals x. Remember, this is the same as natural log, so we can do natural log 10.1 equals x, and this is natural log negative 0.1 equals x. So this gives me x equals about 2.31. Remember, here your argument of a log or a natural log has to be a positive value, so this is going to give you x has no solution. So our answer is just x equals 2.31. We could also solve this just by graphing. So again, I moved everything to one side of the equal sign and set it equal to 0. Taking a look at our graph then, we can see there's one solution, and then I can do intersection or 0 to find that solution. Remember, if you're going to do intersection, you have to have the 0 and the y2. Then from the graphing here, we can see that we have the answer of about 2.31. In this case, obviously, graphing is a little bit simpler than the algebraic method. So back to some log examples. Remember, I'm going to write this log base 10 of x squared equals 4. So I'm going to solve this using my convert notation method. So 10 to the 4th power equals x squared. Remember, we have to square root both sides here to get rid of that squared. We're going to square root both sides here to get rid of that squared. So we're going to get x equals plus or minus the square root of 10 squared, which is going to, or 10 to the 4th, which is 10 squared. So we get x equals plus or minus 100. Remember, we have to be careful about extraneous solutions here. So when I plug this negative 100 in for x, it's actually still fine, because if we do negative 100 squared, when I square that negative, it's going to become a positive. So this is going to be log of 10,000, which will give me 4. So both solutions are acceptable here, and we get x equals negative 100 or positive 100. One more log example. This one is different because it has multiple logarithms in it. The ones we've done previous to this point just had a single logarithm in it. So what we want to do when we have something like this is we want to get one single logarithm on each side of the equal sign with no exponents in front of them. So we have to use our properties of logarithms here. So I'm going to use my properties of logs here. So I'm going to make this natural log the 3x minus 2 times x minus 1. So I'm using that product property, and then on the right side we're just going to use the power rule, and this is going to become natural log x squared. So now just doing some algebra, this is natural log. This is going to give me 3x squared. We're going to get minus 5x plus 2, and then equals natural log of x squared. So then essentially what we're doing is we're going to do the same thing to both sides of this equation. Remember, natural log is log base e. So this becomes e to the natural log 3x squared minus 5x plus 2 equals, and then over here e natural log x squared. So remember, these will cancel each other out. So we'll end up with 3x squared minus 5x plus 2 equals x squared. So I'm going to get this as a quadratic. I'm going to get everything on one side of the equal sign. So 2x squared minus 5x plus 2 is going to be equal to 0, and then we can solve this however we want using our procedures for solving quadratics. So if we use the quadratic formula, we're going to get 5 plus or minus the square root 25 minus 4 times 2 over 2 times 2. From that we get 2 or 1/2. Remember, it's important to check and make sure none of these values will make our arguments negative or 0. So going back to my equation here, if I plug 2 into 3x minus 2, I'm going to get 6 minus 2, which is 4. If I plug 2 into the second argument, 2 minus 1 is 1. And over here, I would just get 2. So 2 seems to be okay. If I plug 1/2 in, 3 times 1/2 is 1.5 minus 2 is going to give me negative 0.5, and I can't have a negative argument. Same thing here, 1/2 minus 1 is going to give me a negative 1/2, and that's not okay. So this is an extraneous solution because it makes my argument, one or more of my arguments, negative or 0. So our answer is simply x equals 2. Remember, you could always solve this by graphing, putting that into your calculator and looking for the intersections or the zeros.